So in the previous video we have just refreshed about atomic models. Now that means, as you know, an atom consists of a central positively charged nucleus. Nucleus consists of neutrons and protons. Protons are positively charged particles. Neutrons are electrically neutral, around which electrons are revolving, which are negatively charged particles. So here, if I say if you consider the hydrogen atom, which consists of one proton and one electron. Nucleus consists of only one proton, no neutrons. Electron is revolving around the nucleus. So therefore, if you remove an electron from the hydrogen atom, what it results? A proton. What is this? It is a nucleus. Therefore, you can say that proton is nothing but it is the nucleus of hydrogen atom. So proton is nothing but what? Nucleus of a hydrogen atom. Right. So when you consider this, let us see the different terms. What are isotopes? Isotopes means elements with same atomic number but different mass numbers. Same atomic number and different mass number. See, when you consider the hydrogen, hydrogen has two stable isotopes. So that is 1H. We are getting to 99.99%. And 2H. Right. This is its percentage is 0.01%. So that means this is called the deuteron. Deuteron consists of what? It consists of one proton and one neutron. Right. So the nucleus, deuterium, right? This is nothing but deuterium. Nucleus of deuterium is called deuteron. So there is one more unstable isotope of hydrogen, that is tritium. 3H. Similarly, the nuclei with the same mass number, same atomic number and different mass number is called isotope. Right. Similarly, nuclei with same mass number but different atomic number, they are called isobars. If the two nuclei with the same number of neutrons, that is called isotones. They are referred to as isotones. So this is just something about isotopes, isobars and isotones. These words will come while studying the nuclear physics. So When you consider the atom as already considered, what is this mass number? Mass of proton plus mass of a neutron. So when you are considering 2, it is almost equal to the mass of the atom, right? So why? Because mass of the electron is negligibly small. Whole mass of the atom is considered to be concentrated in the nucleus. So if I write the atomic mass is equal to m, mass of the atom is equal to m. So what is the nuclear mass then? Mass of the nucleus is equal to how much? Exactly, if you want. Mass of the nucleus is equal to total mass, right? Total mass of the atom, atomic mass, minus total mass of all electrons present in the atom. Let us you take, there are Z number of electrons and me is the mass of the electron, then total mass of all electron becomes Z into me. So this is nothing but nuclear mass. So now when you are considering to this, say consider the nucleus. Nucleus consists of Z number of protons and N number of neutrons. Experimentally, you measure, consider a particular nucleus and measure its mass. Its mass I am writing as ma of Az. This is the nuclear mass. Okay, MAZ, experimentally measured value. Now, as you know, a given nucleus consists of Z number of protons and N number of neutrons. Therefore, what happens to the total mass of the nucleus? Let us you take mp is the mass of the proton, then total mass of all protons becomes Z into mp. Let us you take mn is the mass of the neutron. Then if there are n number of neutrons, total mass becomes n into mn. Then total mass of protons plus total mass of neutrons present in the given nucleus becomes Zmp plus Nmn. But what we think then, experimentally measured value is this, but theoretically calculated value is this. Whether it becomes the same, when you ask this question and when you compare the theoretical value and experimental value, we are observing that experimentally determined mass of the nucleus is less compared with this sum. That means we are observing a difference, Zmp plus Nmn minus Maz. This is equal to delta M. So that means we are observing that there is a difference amount of mass between the theoretical and experimental value. Question is, do we have violated any conservation laws? Answer is no. See, when you are forming the nucleus means you have to bring Z number of protons and N number of neutrons close together. During the formation of the nucleus, there is an evolution of energy. Evolution of energy. That is equal to how much? Delta M into C square. That means this much of energy is lost during the formation of the nucleus. This much of energy is evolved. Because of this, we are observing the difference. This evolution of energy equal to delta mc square, that is called binding energy. That is called binding energy. Now, let us study about the binding energy curve. Okay. So, let us consider the graph in which binding energy per nucleon is taken along y-axis and mass number is taken along x-axis, and just see here you can observe that when the mass number is small, the binding energy per nucleon, okay, that is small. That means binding energy is very small. Then later, after say 20, this increases rapidly. Then around 40, when you reach it, what happens? The binding energy is almost constant of about 8 million electron volt. At higher values of mass number, there is a slight decrease in the binding energy. And also you can observe here and there some less prominent peaks in the binding energy curves. Right. So here you can observe that at higher mass number there is decrease in the binding energy. Why? Because mass number increases means number of protons also increases. Right? Binding energy also can be said that it is the energy needed to separate the nucleons present in the nucleus. These protons and neutrons are called what? Nucleons. As number of protons increases, what happens to the electrostatic force of repulsion between them? That also increases. Because of that, the energy needed to break them is decreases. Therefore, at higher mass number, binding energy per nucleon decreases. And also, you can observe that when you consider the higher mass number element, here you can observe the neutron axis. Say, when you consider 92 uranium 238, what is the neutron number? Say, neutron number is equal to 238 minus 92 proton number, right? So, what happens? 146, right? So, neutron number is excess. When you consider 6C12, 6 protons and 6 neutrons. That means at lower mass number, you can observe there is number of protons is equal to number of neutrons, or their numbers are almost same. But at higher mass numbers, neutron excess is observed. It is because at higher mass number, we are observing more number of protons. So, in order to keep this protons within the nucleus, more neutrons are formed. Therefore, there is large attraction between this neutron and protons. So because of this large interaction between the more number of neutrons and these protons bound to the nucleus itself. Okay. Now, and I told at certain mass numbers we are observing less prominent peaks. These peaks are observed at 20, 28, 50, 82 and 126. Right. That means if the either proton number or neutron number or both, that is equal to 20, 28, 50, 82 or 126, right? Then such elements are more stable compared to other. So therefore these numbers are called magic numbers. So in order to explain this magic number, we are making use of a shell model. Right. This is about binding energy curve. So when you consider what is the shape of the nucleus, right? Whether it is spherical in shape or something else, right? In order to understand the shape of the nucleus, we are using the term electric quadrupole moment. Electric quadrupole moment. It is given by, you have studied this, Q is equal to 1 by E integration 3z square minus square root of R dash into theta dash. See, if the electric quadrupole moment Q is equal to 0, then the nucleus is spherical in shape. If quadrupole moment is greater than 0, positive, then it is a prolate spheroid. Right. Ellipsoid is like this. If Q is negative, then we are observing a oblate spheroid. That is nothing but this. So, therefore, non-zero quadrupole moment gives a measure of departure of the nuclear shape from sphericity. Okay. This is a brief introduction about binding energy and quadrupole moment. In the next video, we will see why we have to study Deuteron, and let us study the Deuteron problem. Thank you.